Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Under acid-catalyzed H+, conditions with heat, delta, cyclopentane can undergo carbocation chemistry. However, the more relevant reaction here is the acid-catalyzed dimerization, oligomerization or ring-opening rearrangement. Actually, the key reaction is the acid-catalyzed ring expansion and rearrangement of cyclopentane under H+ and heat. Moving on to the next step. Identify the starting material. The starting material is cyclopentane, a 5-membered carbocyclic ring with no substituents. Moving on to the next step. Under H+, acid, and heat, cyclopentane undergoes protonation to form a cyclopentyl carbocation. The cyclopentyl cation, secondary, can undergo ring expansion via 1,2-hydride or 1,2-alkyl shift to give a more stable carbocation, or the cyclopentane can dimase. And for the final step. Actually, the reaction of cyclopentane with H+ and heat is a well-known isomerization-dimerization. Two molecules of cyclopentane can react under strong acid conditions to give a C10 product, but looking at the options, all are C7 or C8 compounds, suggesting a different pathway. Re-examining the options, option B is a cyclohexene ring with 2 methyl groups, dimethylcyclohexane, which is a C8 compound. Option D is isopropenyl cyclopentane, C8. Options A and C appear to be C8 as well. The reaction of cyclopentane under H+ heat involves protonation, ring opening and ring expansion. Cyclopentane, cyclopentyl cation, ring expansion to cyclohexyl cation via C to C bond insertion is not straightforward. More likely, cyclopentane undergoes acid-catalyzed isomerization rearrangement. A known reaction is that cyclopentane with UlCl3 or H+ gives methylcyclopentane or cyclohexane products via hydride transfer and rearrangement. However, considering this is a dimerization problem, two cyclopentane molecules, each C5, would give C10 which doesn't match. Looking more carefully, perhaps the starting material undergoes intramolecular rearrangement. Cyclopentane, C5H10 weight, cyclopentane is C5H10, under H+ delta could form a carbocation that rearranges. The answer is B, 3,4-dimethylcyclohex 1Na, a cyclohexene with 2 methyl groups. This is consistent with the ring expansion of cyclopentylmethyl or a dimerization pathway where two C5 fragments combine and lose H2, but that gives C10. Most likely the reaction involves cyclopentane undergoing acid-catalyzed ring opening to a pentyl cation, recyclization, and rearrangement. The cyclopentane ring opens under strong acid to give a secondary carbocation which can recyclase to a 6-membered ring, more stable. The ring expansion of cyclopentyl carbonyl to cyclohexyl cation is well known. With methyl migration and elimination, 3,4-dimethylcyclohex 1Na option B would be the thermodynamically favored product as it has a trisubstituted double bond, more stable by Zaitsev's rule, in a 6-membered ring. A methylcyclopentane derivative keeps the 5-membered ring and is less stable. C has a cyclopentene ring which is strained. D. Isopropenyl cyclopentane has an exocyclic double bond on a 5-membered ring. Option B with a 6-membered ring and internal disubstituted double bond is the most thermodynamically stable product. Therefore, the correct answer is B. Therefore, the correct answer is option B.